Assalamualaikum Mr. Azri. Today, we from group number 1, named Rotor Rangers, will be presenting the group project assignment titled Integrated Power System for a Remote Industrial Facility for the course KM30303 Electrical Power and Machines. So, here is the details of all our group members. We have the presenter, which is me, Andy, the second presenter, which is Enna, the third presenter, which is ALIFF, the fourth presenter, which is MAISARAH, and last but not least, the fifth presenter, which is Muhammad IZZAT NAUFAL. Now, moving on to the first section, which is introduction. The first point being problem statement. Remote industrial facilities often lack access to the national grid and rely on diesel generators, which are costly and environmentally unfriendly. So the facility needs stable power supply for oil extraction machinery, conveyor systems, pumping operations, lighting, and auxiliary loads. The solution offered is a hybrid renewable energy system combining solar PV, hydropower, and energy storage to improve reliability and reduce energy intermittency. The project scope includes load estimation, generation, and storage sizing, transmission and distribution, AC motor selection, and last but not least, motor selection. So on this slide here, we have the next section 2.0, which is power generation design. This slide shows the overall system architecture of the proposed hybrid power system. The proposed system uses a centralized DC bus architecture to integrate multiple energy sources efficiently. Hydropower supplies a stable base load, solar PV handles daytime peak demand and battery charging, and the battery ensures continuous supply during low generation periods. Alright, we are now at slide 2.3, where we are going to talk about the load demand estimation. Here, we are going to discuss about the estimation made for the facility. Alright, so the facility has a peak load of 28 kilowatts with a daily energy consumption of 212 kilowatt hours per day. And for the design margin, we applied to account for system losses, future expansion, and operational uncertainty. A design margin of 20% is applied. This increases the total design energy requirement to approximately 260 kilowatt hours per day, which is used as the basis for generation sizing. Alright, now we are at the next slide, which is talking about the point 2.4 and 2.5, which is the solar PV and hydropower design. So the solar PV subsystem is designed with capacity of 80 kilowatt peak based on an average of 4.5 peak sun hours per day in Sabah and an overall system efficiency of 0.75. The micro hydro subsystem, on the other hand, provides a continuous output power of 7.65 kilowatts. This is calculated using the gross head of 15 meters and also the flow rate of 0.08 cubic meters per second. And for the energy contribution, the hydropower supplies over 70% of the facility's daily energy requirement, improving overall reliability. Alright, now we are at the next slide, which is 2.6, where we are going to talk about the energy storage and load balancing strategy. So for the battery energy storage system, it has a total capacity of 120 kilowatt hours. The purpose of this energy storage system is to support the nighttime operation. It covers an estimated of 80 kilowatt hours usable energy requirement. This is super useful to handle short-term peak load conditions. And for the load balancing strategy, it prioritizes hydropower as the base load, followed by solar PV for peak demand and battery charging, with the battery supplying power during generation deficits.
Assalamualaikum, my name is ENNA NADIRAH binti JALIE, matrix number BK23110231. I am presenting my part, which is 3.0 transmission and distribution. So because our palm oil facility is located in a remote area, without grid access, we need a system to distribute power internally and export the energy to a village several kilometers away. So our design focus here is to minimize energy loss while ensuring maximum safety and reliability. So for our voltage level selection, to achieve high efficiency, we utilize two different voltage levels. Within the facility, we use a low voltage level of 415 volts, which is ideal for our industrial motors. However, to transmit power to the village, we step this up to 11 kilovolts. And we've selected two transformers for this task. Step-up transformer at the facility increases the voltage to reduce current and heat loss during transmission. And at the receiving end, a step-down transformer brings it back to 450 volts for safe use by the villagers. Next, transmission line and conductor selection. So for the physical delivery of the power, we opted for an overhead transmission line because this is the most cost-effective and practical solution for a rural environment. And then the choice of conductor, we are using aluminum conductor steel reinforced, or in short ACSR. This conductor is a hybrid. The aluminum layers provide excellent electrical conductivity, while the central steel core provides the high mechanical strength needed to span long distance with minimal sag. Moving on to protection devices, the table shown in the slide contains list of protection devices or equipments. Because safety is our top priority, so we have implemented a multi-layer protection scheme. So circuit breakers and relays are installed to detect and isolate short circuits or overloads. And then because this is an outdoor rural system, we also included lightning arresters and surge protection devices. So this will protect our transformers and equipment from high voltage transients by directing them safely to the ground. So overall, the transmission and distribution network can be seen in this single line diagram. It starts at our hybrid generation system and passes through the 415 volts to step up transformer, travel across the 11 kilovolts transmission line, and finally reaches the village via the step down transformer. So this integrated design ensures that our facility remains productive while providing sustainable energy to the local community. That is all from me. Thank you.
Assalamualaikum to Dr. Azri. My name is Muhammad Izzat Naufal bin Abdullah. Matrix number BK2311023. I'm going to present about SC motor selection and control. Okay, for SC motor selection and control, for our facility, we standardize on using the 3-phase squirrel cage induction motors. Why? Because in a remote, off-grid location, we need motors that are rugged and require minimum maintenance. For our specific machines, we choose the motors based on the work they do. Okay, first one is for oil extraction. We need high torque and constant speed. This is because crushing a palm fruit is heavy work. The motor must be strong enough to keep a steady pace without slowing down under the heavy load. Okay, the second one is for pumps and conveyors. We focus on efficiency, and these machines don't always need to run at full speed. By using variable speed control, we can slow them down when they are not busy. This saves a lot of electricity and makes our system much more efficient. Moving on to the next part, which is the selection of AC motor. The first one is we have the oil extractor machinery. For this high demand application, we have selected a 3-phase squirrel cage induction motor, which I have told you before. For the performance, it delivers a rated power of 30 kilowatt, making it the most powerful unit in this group. For the electrical specification, it operates at 415 volts at 50 Hz with a rated speed of 1470 RPM. For the key detail, notice it shows the S1 duty class. This means the motor is designed for continuous duty, allowing it to run at a constant load for long periods without reaching thermal instability. This is essential for steady oil extraction processes. Next is our pumping system. While this is also used a 3-phase induction motor, we have integrated a variable frequency drive, known as VFD. For the power, this is an 11 kilowatt motor operating at 415 volts. The advantages, by using a VFD, we can control the motor speed to match the fluid flow requirements. This significantly reduces the energy consumption and prevents water hammer effects in the pipes by allowing for smooth starts and stops. The third one is conveyor system. It's similar to the pump. This uses a 3-phase induction motor with a VFD also. This is our small unit, which operates at 5.5 kilowatt, reflecting the lower torque required to move the belt compared to the extraction or pumping. For the speed range, the VFD is critical here because it provides a wide speed range of 500 to 1500 RPM. This allows the operator to speed up or slow down the production line based on the volume of material being moved, ensuring the system remains flexible and synchronized with the rest of the facility. Continue to the next slide, which is motor starting methods and protection scheme. One of the biggest challenges in this system is managing the inrush current when the motor starts. To handle this, we use two different strategies. For our largest motor, which is the 30 kilowatt, we use a star delta starter. This effectively drops the starting current to just 1/3 of its normal level, which preventing power surge that could trip our microgrid. For the pumps and conveyors, we have integrated variable frequency drives. These aren't just for starting, but it also allows us to precisely control the motor speed by adjusting the frequency. This off-start capability prevents mechanical wear and ensure the system lasts longer. To ensure the facility stays operational, we must have the layers of protection. For the first one is the thermal overload relays to stop the motor if it gets too hot. For the second one, molded case circuit breakers for short circuit safety. And the third is the phase failure relays, which are critical in remote areas to shut down the motor if one phase of the supply drops out. This keeps our equipment safe and our maintenance costing low. Okay, moving on to my final part, which is the performance calculation. To make sure the system operates efficiently, we analyze the performance of the 30 kilowatt oil extraction motor. For the rated current, based on the formula stated, we calculate, and the motor shows the approximate current, which is 55 ampere at full load. For the top output, using the stated formula, the motor generates at 195 Newton meter of torque at its rated speed. Okay, the analysis, this high torque output at 1470 RPM ensures the system has sufficient power to handle heavy-duty extraction demands reliably. That's all from me. Thank you.
Next is about power electronic integration. Power electronic enable efficient energy conversion and control in this off-grid palm oil processing facility. They are important to maintain stable voltage, stable frequency, and reliable operation when the load and renewable energy generation change. This system uses a DC bus architecture as the central integration point. The solar PV system generates DC power and is regulated using an MPPT charge controller to maximize energy extraction and protect the system. The micro hydro system generates AC power, which is converted to DC using a rectifier to allow hybrid operation with solar PV. A battery energy storage system is connected through DC-DC converter to store excess energy and supply power during load changes, improving system stability. The stabilized DC bus voltage is converted into three phases AC using a DC AC inverter. This AC power supplies industrial loads such as motor, pump, conveyor, and lighting. Variable frequency drive or VFD are used for motor control to provide soft starting, reduce inrush current, and improve energy efficiency. When excess power is available, it is transmitted to a nearby village through a step-up transformer and a long-distance transmission line. Power electronics ensure that voltage and frequency remain within acceptable limit before transmission. Overall, power electronics improve energy efficiency, power quality, system flexibility, and reliability. They are also reduce electrical and mechanical stress on equipment, making the system suitable for off-grid industrial application.
Okay, hi, Assalamualaikum everyone. My name is HAKIMI. I'm the third presenter of the list, so I will talk about system analysis. Okay, first, load flow analysis. During the day, solar PV and hydropower produce more power than the facility needs, so extra energy is stored in the battery. At night, hydropower and the battery supply the load when solar power is not available. Even in the worst case condition, the battery can support the system without load shedding. This shows that the system can supply stable and continuous power. Okay, second, fault analysis. This analysis is done to ensure system safety. If a fault occurs at the AC distribution site, circuit breakers quickly isolate the fault to protect the inverter and loads. For motors, thermal and overload protection prevent damage during abnormal conditions. For the DC bus, DC fuses and breakers protect the battery and power electronic components. This protection ensures safe and reliable operation. Okay, for the last one is system efficiency. The system efficiency considers losses from generation, batteries, inverters, and cables. Using hydropower continuously help reduce battery usage and energy losses. In conclusion, the system operates safely, efficiently, and reliably, and it is suitable for a standalone remote industrial facility.
We have now arrived at the final slide of this presentation, which is 7.0 conclusion. In conclusion, the proposed solar hybrid power system successfully meets the facility demand under all possible operating conditions, which are normal, peak, and worst-case operating conditions. And for its sustainability aspect, it reduces reliance on fossil fuels through a resilient hybrid solar hydro battery system. Moving on to its overall impact, it ensures reliable industrial operation while also enabling the excess power supply to a nearby rural village, greatly enhancing the electrification capabilities for the rural village. And the final remark of this project is that it achieves an overall system efficiency of 15%, demonstrating a technically sound and sustainable solution for off-grid applications. That's all from us. Thank you for listening.